Sí, sí, se te escucha bien.
Venga, gracias. Okay. For today's session, we'll work with the EH1 core, which is described in detail in this section, in this video, that you should all have seen already. If you haven't been able to watch the video, you can do it now, because it is the background for developing the exercises proposed for today's session. In this video, we use these slides where, as I was saying, the EH1 core is explained in detail. Well, first, some introduction to the VIR processors is given, but then the EH1 processor, which is the core that we're using in the course, is explained in detail. So I won't repeat now what the video explains. It makes no sense. It's better that you look at the video carefully. You repeat those parts that you don't understand initially, and you ask me about those things that are not clear or you don't understand. The EH1 is a two-way superscalar processor. It can execute up to 2 instructions per cycle. It includes 4 data paths, 2 for integer instructions. It has an arithmetic logic unit in the first stage of the execution that is able to do arithmetic logic instructions. It has 1 data path for multiplications, integer multiplications. It has another data path for load store instructions. And finally, it has an out-of-pipeline path, which is for the division, and which is not pipeline, as I was saying. It requires up to 34 cycles to compute integer divisions. Using these 5 data paths, up to 2 instructions can be executed. Obviously, not always, not in every cycle, the processor will be able to execute 2 instructions per cycle due to the different hazards that are present: structural hazard, data hazards, and control hazards. As for the first, structural hazard, for example, we can have one of such kind of hazards when 2 multiplications arrive at the code at the same time. In that case, given that we only have 1 data path for multiplications, the second one will have to wait in the decode stage until the first one progresses through the pipeline. The multiplier is pipelined, so once the second instruction advances, once the first multiplication advances, in that case, the second one can start execution right after the first one. They will execute back to back, but not at the same time. So that would be an example of an structural hazard. In the slides, more examples are given, and also in the examples and exercises, more of these situations are proposed that you should analyze. As for the data hazards, many different situations are possible. But for example, if we have multiplication followed by an add instruction, which uses as an input operand the result of the multiplication, the second instruction, the add, will have to wait for some cycles until the multiplication has its result available. And that will happen at the third stage of the multiplication, because multiplications are pipelined into 3 different stages, because it's a demanding operation and it requires 3 stages. So until the third one, the result will not be available. At that moment, the add instruction, which depends on that multiplication, can start executing, but not until then. So two bubbles will be introduced in the processor for dealing with this data hazard. Okay. Finally, control hazards are introduced for branch instructions, given that the branch instruction can go or can continue through 2 different paths. taken and not taken, and the next instruction is not known until the branch is resolved, until the branch or jump is resolved, and that happens in the X1 stage. So control hazards will also introduce a delay unless we use a branch predictor. You probably all are at least know what a branch predictor is. The branch predictor lets us predict the direction of the branch, whether it will be taken or not taken, and also, in case of taken branches, the destination of the branch. So this processor includes two possible branch predictors, one which is quite naive, which is a non-taken branch predictor. Branches are always predicted as not taken. And the second one, which is more complex and one, which is the G-share branch predictor, and which provides a higher accuracy than the other one. Okay. Anyway, after a branch, there are many cases when there will be bubbles introduced in the pipeline for dealing with that hazard. Okay, so all those situations are explained in detail in the slides. So please look at the video, try to understand all those cases, and then you'll be ready to do the guided examples and the exercises. Going back to the GitHub, after you watch something else I wanted to mention about these slides, at the end, you also have something which is important because you'll use it in the exercises, which is that we can configure several features of the EH1 processor. And that can be done in software using two control instructions that are explained in the slides and also in the examples, and that allow us to configure the processor with the different features enabled or disabled, or some of them at least. For example, we can enable or disable pipeline execution. We can enable or disable branch prediction. Well, a branch predictor will always be enabled, but it can be the simple one or the complex one. So the non-taken, always not taken branch predictor, or the G-share predictor. We can configure that also in software. We can also enable or disable dual issue execution, the superscalar execution, something which is called secondary ALU, which is another feature of this processor, which is explained in the video, and some other things. Okay, so this is important because in the exercises we'll ask you to analyze and measure the performance under different configurations of the processor. Okay. Any question about these slides and the EH1 core details? Okay, so after you watch the video and you understand the EH1 microarchitecture in detail, you are suggested to do guided examples about the two simulators that we'll be using in this session. In this session, you don't need to use the board. You will do all the work in two simulators. So first, before starting to work in the exercises, you should look carefully at these examples or guided examples about the two simulators that you will use. You have already tested these simulations at the beginning of the course, but now you're provided with more examples about their use. So the first one is the RVFPGA pipeline simulator. That simulator allows us to analyze the microarchitecture of the EH1 processor. It will show us the internal signals and the internal operation of the different stages of the core and allows us to visualize an example program executing during the different cycles of execution in this core. So the first example provides a given program, which is this one, 2 multiplications, 1 add instruction, and 1 branch. So this is a loop. It's an endless loop, which repeats these 3 operations. So when we follow these steps, will be a new window will open, which shows us something like this. And this represents the backend of the processor. It's a simplified view, of course. It's not as detailed as the one shown in the slides, but the information is the same. Okay, so this is the detailed figure, okay, for the backend of the processor. Let me remind you, it has the processor has 9 stages. The backend, the front end, which is in the previous slide, has 3 stages: fetch 1 and fetch 2, because fetch instruction fetch is divided into stages, and the align stage. Then the backend, which is the part that we view in the simulator, we cannot view the 3 initial stages. They exist, of course, but we cannot analyze them in the simulator. The simulator only shows us the final 6 stages, the backend of the processor. It has the decode stage, 3 execution stages, 1 commit stage, and the write back stage, well, where the results are written back to the register file. Okay, so the simulator shows a simplified view of those 6 stages. This is the decode stage, the first execution stage, second and third execution stages, commit stage, and write back stage. Okay, and you can view here the 4 data paths. Note that the divide path is excluded, is not shown here. Okay, we won't have divisions in our in the programs that we'll analyze in the course, so we don't need to visualize it. So it shows the 4 data paths, which are the same here: I0, mul, ls, and I1 pipe. So I0, mul, ls, and I1 pipe, and these are the main signals belonging to each stage of each pipe. So for example, oh sorry, can you hear me?
Yeah, we can hear you.
Yeah, we can.
Okay, so
this page just opened by mistake, I believe.
Okay, there's a problem with this page.
Perhaps you clicked on the image or something.
Yeah. Yeah. That must be. So I was saying, we can view here the main signals of each stage and each pipe. So for example, for the I0 pipe, we can see here A and B, which if you go to this figure, you can see they are the inputs to the this is A and B. It's a bit small, but this is A, this is B. So these are the signals shown in the simulator. So if I have A equal to 0, B equal to 2, it means that here my operands for the ALU would be 0 and 2, and in the next cycle I will see the ALU operation of 0, whatever, 2, plus or and or whatever, and the result. So in the next stage I will be able to see the whatever operation, in this case an addition, 0 plus 2, and the output of the ALU, which is 2. Note that these are 2 different cycles. Okay, these are the instructions in cycle I or whatever, and these are the instructions in cycle I plus 1. Okay, okay. So this would be the result of the addition in this case. Okay, and the same for all the stages and all the data paths. So for example, let me pick an example of the write back stage. For example, these 3 signals would be the inputs to the register file. to the first port of the register file. This would be the second port. Okay, we remember that we can do up to 2 writes to the register file, given that we can execute up to 2 instructions per cycle. So this would be the first port. So this is the address I want to write to, the enable or disable, and the data I want to write to. And if you go to the other figure, you can see that in the register file, we also have W address 0, WD1 0, and well, the enable is not shown here, but we have an enable signal for each of the 2 ports, enabling or disabling the write of the data. Okay, so this shows the information for the main signals of the core, and I can view the different cycles. There is a button that lets me advance cycle by cycle, so I can see how the program goes through the EH1 core, the backend of the EH1 core. Is this clear? Any question about the pipeline simulator? Okay. So please start by, if you haven't yet, start by doing, well, after you see the video, do this example in your own simulator and try to understand it and try to improve your understanding of the core. What you've seen in the video, you can understand it better when doing all these examples. Okay, then after this guided example that you should do carefully on your own, you have another guided example or exercise in this case, which proposes another program and the analysis that you should do in these cases. This is an exercise which is provided with the result, and the idea is that you understand what we are asking you to do in the exercise. So after this, when you go down to the exercise part, this exercise 1 should be resolved in the same way as that guided exercise. Okay, it's just the guided exercise is an example of what you should do in this first exercise. Okay, so please again go through this solution carefully, try to understand it, and try to understand what we're asking you to analyze in the program. We ask you to analyze the different hazards, structural data and hazard, and control hazards, to explain them, to show in the simulator how they are handled, to compute the timing diagram, something like this. You can draw this by hand in a paper and do a photo. You can do this in an Excel. You can do whatever you want, but it should show the timing diagram of the program executing in this core. Okay, one way or the other. You should include these arrows for showing the data hazards and the bypasses, how they are resolved through the forwarding bypass paths and so forth. And finally, you should compute the CPI of the program. Okay, so this is an example of how you should resolve exercise 1 using the RVFPGA simulator. Okay, we don't ask you to include all this in the report, in the final report, but only the 2 exercises. Okay, this is just for guidance and for you to understand the core and to understand what you're asked to do. Okay, any question about these RVFPGA pipeline examples? Good. Finally, you will be using another simulator tool provided with the RVFPGA package, which is the RVFPGA trace simulator. You probably are all used to do this kind of simulations in whatever HDL that you've used during your degree or you use now in your job. This is a simulator that allows us to visualize the signals of the core, but in a different way. The previous simulator, the information is the same we had in the previous simulator. The previous simulator is prepared to show the main signals of the core, and the same, I can use this simulator for the same, but it's obviously more flexible. It doesn't, but less visual. You don't have the drawing of the core, but you have something like this. Okay, a diagram that shows the evolution of each of the signals. The internal signals of the core. So, for example, again, you're given an example that you should analyze, and it's executed in the RVFPGA simulator. And it's a very simple example that allows us to understand how the simulator works. We only intend to analyze here an add instruction, how an add instruction is executed inside the core. So we are including the main signals related with the add instruction, which are, for example, the instruction register. This DEC I0 inst D is the instruction register. So this is the encoding of the add T3, T3, T4 that we have in our example. This would be the PC, okay, the address where the instruction is stored at memory. These should be the addresses of the registers that are input, that constitute the input operands for the instruction. So in this case, T3 and T4, which are X28 and X29. These are the values contained in those registers, 7 and 1 in this case. These are the inputs and outputs of the ALU, which in the next cycle computes the addition. So 7 plus 1 is equal to 8 in the output. And then some cycles later, the result of the addition is written in the register file. Okay, so the input port for the right input port to the register file provides the corresponding signals to this addition. 8 is the data, 28 is the register where we want to write. So in the next cycle, the register stores that value. Okay, so again, you should first analyze this guided example carefully, understand everything, so that you will be able to resolve exercise 2, which using the RVFPGA trace simulator asks you to analyze other arithmetic logic instructions. Okay, they are very similar to the add instruction, but they have some small details, specifically in the computation of in the ALU, and you should analyze these instructions. Note that you only need to choose one among these 3 instructions, one among these 5 instructions, and only one among all these immediate instructions. Just pick one, and one, and you perform the same analysis given in the guided example above. And finally, in this exercise 2, you're asked to analyze how the ALU is programmed in Verilog. Okay, you should try to understand how it is implemented in this module. This module can be found in the sources of the SOC, and you have to try to understand its main operation. Not all the details, but at least its main details about the execution of the different instructions. Okay, so try to understand the Verilog module as much as you can and explain it in the report. Okay, so this is the work for today. Any question? No questions? I'll stop recording now. Okay, thank you, Pau. where can I do this? Here. Stop recording.